Welcome to this explainer. Today, we're going to fall down a bit of a mathematical rabbit hole. We're going to figure out what truly happens when things grow and shrink. Now, I know it seems like a super simple concept, right? You make something bigger, it gets bigger. But as we're about to see, the geometric reality of scaling is absolutely full of surprises that will totally challenge your everyday intuition. Just look at this enchanting, fractal-like Romanesco broccoli. I mean, it's absolutely beautiful, isn't it? Nature is just packed with these intricate, scaling patterns. And this image perfectly frames our deceptively simple opening question. What actually changes when something grows? Does the whole thing grow at the exact same rate? Well, to really figure this out, we need to build our understanding step by step. So let's kick things off with the magic of growing, specifically navigating one-dimensional space. Let's start somewhere comfortable, a nice linear concept where things behave exactly as you'd expect them to. We'll dive into this by nailing down our core vocabulary first. The absolute foundation of everything we'll talk about today is the scale factor. This is literally just the number by which every length is multiplied, proportional scaling. So if our scale factor is 2, a length just doubles. A 3-unit line segment becomes a 6-unit line segment. It's a very straightforward one-dimensional rule. Your new length is just the old length multiplied by the scale factor. Easy, right? But here is the trap that catches so many of us. If we enlarge a model so that every single length is twice as long, does the amount of surface it covers also become twice as much? Does the physical space it occupies just double? I actually want you to pause for a second and predict what happens before we fall any deeper into the geometry. All right, let's step into flat worlds and squares. Prepare yourself for the 2D surprise. We really need to dramatically slow down our pace right here as we enter the second dimension. This is the flat world of area. And honestly, it's where our initial intuition just completely fails us. Let's map out the surprising reality of two-dimensional growth. It is so incredibly tempting to say, well, the length doubled, so the area must have doubled. But that completely ignores how area actually works. A scale factor acts in 2 independent directions, horizontally and vertically. So if you double the dimensions, meaning a scale factor of 2, you multiply the horizontal by 2 and the vertical by 2. 2 times 2 is 4. Doubling the lengths actually makes the area 4 times as large. And if you triple the lengths, well, 3 times 3 means the area is 9 times as large. To really build our mathematical literacy here, we have to anchor our reasoning in the unit square. Instead of just blindly memorizing length times with formulas, we need to focus on sense-making. Area simply measures how many of these little unit squares are needed to cover a region without any gaps or overlaps. When you scale up a shape, you are essentially scaling up every single little unit square inside of it. Now, what about the weird stuff? Let's talk about conquering the strange, because irregular shapes actually don't matter. What happens when we step away from those perfect squares and rectangles? When we encounter bizarre, irregular shapes, like a totally strange island map or a random splash of paint that definitely don't fit into a simple formula. Let's compare 2 ways of thinking about this. On one hand, relying strictly on formulas like area equals length times width completely fails the second you hit a highly irregular boundary. But on the other hand, we have piece-by-piece reasoning. By deeply understanding that any shape can be covered with tiny unit squares, we realize the basic meaning of area never changes. This conceptual understanding gives us the superpower to conquer absolutely any shape, no matter how weird or jagged the edges are. So the crucial point is this beautiful logic. If you scale some weird irregular island map by a factor of 2, every single tiny piece of that map, every single unit square, becomes 4 times as large. Therefore, without needing a single complex, headache-inducing formula, we know with absolute certainty that the entire strange shape must also become exactly 4 times as large. The irregular boundary literally does not change the mathematical law. And this brilliantly illustrates how incredibly useful this is in the real world. Imagine a graphic designer needs to scale up an irregular company logo that covers 12 square centimeters. They use a scale factor of 3. We don't need some crazy calculus equation for the logo's weird curves. We just know that every small square inside it is enlarged in 2 directions. 3 times 3 equals 9. Every single piece of area is 9 times larger. So 9 times the original 12 square centimeters gives us a new area of 108 square centimeters. Boom. This piece-by-piece reasoning is basically a mathematical superpower. All right, brace yourselves. We're entering the 3rd dimension. Get ready for the volume explosion. We are officially leaving the flat world and crossing into 3D. This is where volume takes over, measuring the number of unit cubes needed to fill an object. And this is where the math truly explodes. In 3 dimensions, a scale factor of 2 doesn't give you 2, or even 4. It yields an astonishing 8. Because the change is happening in 3 independent directions, length, width, and height, we calculate 2 times 2 times 2. Doubling every linear dimension makes the total volume 8 times as large. And this explosive scaling math actually grounds itself in biology. It literally explains why large animals cannot simply be scaled-up versions of small animals. Think about it. If you took a tiny mouse and magically doubled all its dimensions with a scale factor of 2, its volume, and therefore its body mass, would multiply by 8. But the cross-sectional area of its legs, the actual bones supporting all that weight, only grow in 2 dimensions, meaning they only multiply by 4. Giant enlarged Alice in Wonderland creatures would literally collapse under their own weight, because their mass grows drastically faster than their bone strength. No way around the math. Let's bring this rabbit hole back to modern reality. Here comes the 3D printing surprise, and its real-world consequences. Let's see how this volume explosion builds a massive hidden cost right on your desk. Imagine you have a cool little 3D model that uses 18 grams of plastic filament and costs about $3 to print. You decide you want it to sit nicely as a centerpiece, so you enlarge it by a scale factor of 2. To your eye, it only looks twice as big. But because volume scales by the cube of the scale factor, the actual volume is 8 times as large. Suddenly, you need 144 grams of filament, and your cheap $3 print just exploded into a $24 surprise. Now, full disclosure, I do have to add a quick practical caveat here. This factor of 8 is a mathematical model for a fully solid object. In reality, your actual 3D printing costs might vary because of how the internal structures are built, things like your infill percentage, the thickness of the walls, or the extra support materials used. But the mathematical baseline rules still gives you a critical warning. Volume grows incredibly fast. So what's the big takeaway? It's all about the power of understanding, sense-making over memorization. Ultimately, the goal of this entire explainer is true sense-making. By deeply understanding this geometrical reality, you are no longer blinded by the limitations of rote formulas, and you for sure won't be caught off guard when you try to scale up a design, a recipe, or a real-world project. To sum up our whole journey, if you have a scale factor of k, length scales by k. Area operating in 2 dimensions scales by k squared, and volume operating in 3 dimensions scales by k cubed. A seemingly tiny change in linear length creates a much larger proportional change in surface area and an absolutely explosive change in volume. I want to conclude by leaving you with a really provocative thought to chew on. We've spent all this time talking about growing, but how does this exact same geometric intuition apply when we drink the shrinking potion? What happens to the math, the area, and the volume when your scale factor is less than 1? Say, reducing a photograph to half its size. I highly encourage you to apply that piece-by-piece reasoning we just learned and see exactly where the math takes you. Thank you so much for falling down this scaling rabbit hole with me today.